Radian measures of an angle are actually very powerful in application because of its geometric interpretation as the length of the arc is the radius times the radian measure. And that's this formula right here. This comes directly from the definition of radian measure, where we had theta is equal to S over R. And so this is nice because it allows us to compute an arc length swept out by a portion of a circle by simply taking the radius of that circle and multiplying by the angle when measured in radians. So here's a quick example. It's a very straightforward concept. A circle has a radius of 4 inches. We want to find the length of the arc intercepted by a central angle of 240 degrees. So I'm just going to go ahead and draw a picture here. We've got our circle, and we are saying I've got a central arc of 240 degrees, and that's going to be, something like that right there. That's 240 degrees. Okay. Well, we have the formula that the arc length S is equal to the radius times the angle theta when theta is measured in radians. And this is the key that's the key that theta has to be measured in radians. Our angle here at 240 degrees, that's not in radians yet. And so we're going to go ahead and convert that. So to get from 240 degrees to radians, we multiply by pi over 180 degrees. And this is then, we'll just simplify this. And this simplifies to be 4 pi divided by 3. So that's the angle theta. And we, of course, know the radius is 4 inches. So the arc length is 4 times the 4 pi over 3. And that gives us 16 pi over 3. And that's going to be in inches. We're talking about the length of the arc. And our radius was measured in inches. So you can see that with the radian measure of an angle, this is a very, very quick way to compute that length of the arc. So that's the distance from here all the way around the circle to there. That's that length. Another nice application of angles measured in radians is the area of a sector of a circle. And this is where, again, if you have a circle and you look at you've got a sector of that circle, whatever, okay, we're looking for this area here, okay, where this angle here is theta. And this formula, this comes directly from the fact that we know that the area of a full circle is pi times r squared. And all we need to do is take a portion of that, where we know this angle theta. If measured in radians, we know a full circle is 2 pi radians. And so really that's all we're doing. We're taking the area of a circle, pi r squared, and then taking a portion of that, which is theta divided by 2 pi. Okay, this is what portion of the full circle of 2 pi radians is our angle theta. And you can see that the pi cancels, and you end up with a 1/2 r squared theta. That's this formula given. So it's a very, very simple formula to give us the area of a sector of a circle. So let's look at this example here. A sprinkler on a golf course fairway sprays water over a distance of 70 feet and rotates through an angle of 120 degrees. Find the area of the fairway watered by the sprinkler. Well, that's pretty much what I've drawn right here. I've got a sprinkler head right here, and it sprays this central angle of, and I'll go ahead and get rid of that, sprays an angle of 120 degrees, okay, and it sprays 70 feet. We'd like to find the total area that it sprays here, okay? And so we can use this formula, but we do need to do a little conversion because this formula only works when theta is measured in radians. Our angle here is measured in degrees, so we need to convert from degrees to radians by multiplying by pi over 180 degrees. And this simplifies as 2 pi divided by 3. So that's our angle, theta. And our radius r is that 70 feet. So we can plug that in to get the area. 1/2 times 70 squared times the angle, 2 pi divided by 3. And we can, well, the 1/2 and the 2 will cancel. And we have 70 squared, which is 4,900 times the pi over 3. And this is going to be, this is an area. Okay, we squared this 70 feet, so the units on this are feet squared. And if you wanted, you could type that into a calculator to get a decimal approximation, but I'm going to go ahead and leave it as that.